Okay, any questions do you want to ask? Okay, so if you don't have any questions, let's look at the electric field created by a very thin disk. So we have this disk. That has the radius r, and it has a total charge q. Now let's first try to calculate the electric field at an arbitrary point. First, let's stick with an arbitrary point. Then, once we have the general expression, rather than trying to work out some integrals, we will take a simple case. We know the general expression for the electric field at a given point in terms of the charge density. d cubed x, rho of r prime, r minus r prime divided by r minus r prime length cubed, and we have the 1 over 4 pi epsilon 0. Given the volume charge density, this is always the expression for the electric field. We had evaluated rho of r, and we said we had calculated it over here. This is our charge density. So we just put it in the above expression. E of r is equal to 1 over 4 pi epsilon 0. This q over pi r squared is just a constant. We can write it in cylindrical coordinates. In cylindrical coordinates, it would just become r dr from 0 to infinity, d phi from 0 to 2 pi, dz from minus infinity to infinity, Dirac delta of z prime, Dirac delta of r minus r prime divided by its cube, magnitude cube. No, not Dirac delta, it's this theta r minus r prime. Now I can simplify it a bit. This Dirac delta z prime already allowed me to evaluate the z integral, and once I evaluate the z integral, I should put 0 wherever I see some z prime. So that is r prime, phi prime, and z prime. Now, this expression over here also depends on z prime, although it's not explicitly seen, but I will still evaluate the z prime integral, keeping in mind that wherever I see a z prime after this step, then z prime is equal to 0. So this is equal to 1 over 4 pi epsilon 0, q over pi r squared. Now the r prime integral, this step function tells me that the contribution from the r prime integral only comes from 0 up to capital R, so it doesn't really go up to infinity. So it starts from 0 and it goes up to capital R of the r prime times r prime. Phi integral just gives me 2 pi. Z integral just gives me, well, 1, but after this step, z prime, wherever I see a z prime, it should be 0. It should be 0, yes. And, well, that's basically it. Let's make some simplifications. Q over 2 pi epsilon 0 r squared, 0 to r of the r prime, r minus r prime divided by r minus r prime cubed. Again, just a bit of a complicated notation. R prime over here is not equal to the magnitude of this R prime vector. R prime is essentially x prime squared plus y prime squared if we use the x, y, z coordinates. Now we need to write these expressions also in terms of, well, the r coordinate and the r prime coordinate. Well, in spherical coordinates, r prime vector, any vector in fact, will be r in the r hat direction. Well, here let me go back to the rho hat direction. Plus z in the z hat direction. This is the any vector. I can write any vector in this form. Again, I would remind you what the rho hat and z directions are. If you take any vector over here, then to find the z coordinate, you just draw a perpendicular line to the z-axis. And this is the z-coordinate of that point. And you draw a perpendicular to the xy plane. You take the projection on the xy plane, let's say at this point, and connect it to the origin on the xy plane. So this is what I call r, and this unit vector here is what I call the rho hat vector. These are the definitions of r over here. R is the length of this point. It is projection on the xy plane. The distance of the projection on the xy plane to the origin, this is r. Rho hat is this vector on the xy plane. And z is the usual Cartesian z coordinate. R prime is similarly, this will be r prime rho hat. Well, this r prime over here is this r prime over there. They are the same, this r prime and that r prime. And, well, we should have a plus z prime in the z hat direction, but by evaluating the z prime integral above, here, we evaluated the z prime integral, and this Dirac delta told me that wherever I see a z prime, I should put a 0. So the z prime is just 0 in the z hat. So basically, this is the point that is creating the electric field. Since the charges are only on the disk, the points creating my electric field should be on the disk, which has the z coordinate equal to 0. And this is the point at which I'm evaluating the electric field. Now, r minus r prime, this is a vector I will need. This is equal to r minus r prime in the rho hat plus z in the z hat direction. And I will also need its magnitude. Its magnitude is square root of r minus r prime squared in the rho, no, not in the rho hat, plus z squared. This is the magnitude. So the only thing left is I need to just put these vectors into my integral that will give me the electric field over here. So I already wrote this vector in terms of r prime and r. And I also wrote the magnitude over here, so I just put them over here, evaluate the r prime integral if I can, and I'm done. So let's see. I made a mistake though. Can you see my mistake? What is the rho hat vector? Can you write its explicit form? Let's say this angle over here is phi. What is the rho hat vector in terms of x hat and y hat?
R cosine phi.
Now, rho hat is unit vector. So it is
It's I hat cosine phi plus j hat sine phi.
so rho hat is a function of phi. Do you agree? But if rho hat is a function of phi, here you see this vector over here depends on rho hat. You see, we had calculated that vector, and it depends on rho hat, which is a function of phi. But here what I did was I just evaluated the phi integral and said that it was just 2 pi. That is my mistake. It's not 2 pi. I don't know. There is a phi dependence over here, and without that phi dependence, I cannot, without explicitly writing that phi dependence, I cannot integrate the phi. So that is my mistake. So let me correct it. I don't have a 2 pi over here. That is still a phi prime integral. So there is no cancellation over here. I can still evaluate the z integral. There is no problem with that. So this is 4 pi squared. So let me just take that expression. This is the electric field at the point R. Q over 4 pi squared epsilon 0 r squared from 0 to r d r prime from 0 to 2 pi d phi prime 1 over r minus r prime squared plus I made one more mistake. You see, rho vector depends on where, rho hat vector depends on where I am evaluating it. So if I change the point at which I am evaluating the rho vector, then it changes. So if I'm evaluating at the point R, so let's say this is my z-axis. Let's just imagine my R vector is over here. At this point, rho hat vector is this vector. But R prime, we are integrating over the R prime. It can be any vector on my disk. But at this point, rho hat vector is pointing in this direction. It's a different vector. It's not the same vector as the rho hat vector over here. At every point, rho hat vector is a different vector, because every point will have a different phi, and we just said that rho hat vector depends on phi. So when I'm writing R, the rho hat vector has one value. When I'm writing R prime, rho hat vector has a different value. So these two expressions are not correct. Now I will make one simplification. Rather than trying to deal with complicated integrals, I would rather just set, I'm looking for the electric field on the z-axis. Well, on the z-axis, that is when R is on the z-axis, small r is just 0. Because remember, small r if you look at this definition of small r, it is the distance from the z-axis. This is small r, this is small r, this length over here, it's the distance from the z-axis. So if I choose a point on the z-axis, the r coordinate of that point is just 0. So r vector is just some z along the z-axis. Now this will simplify my life. If this is my r vector, r minus r prime vector is equal to minus r prime rho hat prime plus z in the z hat. R minus r prime magnitude is equal to square root of r prime squared plus z squared. So I can just put it over here. R minus r prime vector was minus r prime rho hat prime plus z in the z hat divided by square root of r prime squared plus z squared cubed. Okay, this is the electric field. Of course, we need to evaluate these integrals. Now, phi dependence here is explicit. Phi dependence, r prime doesn't depend on phi, z doesn't depend on phi, z hat doesn't depend on phi. The only thing that depends on phi is rho prime, rho hat. And rho hat, as your friend has pointed out, has this expression over here. What is the integral of cosine phi from 0 to 2 pi? 0. The integral of sine phi from 0 to 2 pi? 0. So the integral of rho hat prime as a function of phi prime from 0 to 2 pi, this is 0. So what remains is only the part that is in the direction of z. So the electric field on the z-axis, that is x is equal to 0, y is equal to 0, z is equal to q over 4 pi squared epsilon 0 r squared. Now, we know that rho hat integral is 0. Nothing else depends on phi. Now I can evaluate the phi integral. That will just give me 2 pi. Integral from 0 to r of the r prime squared divided by r prime squared plus z squared to the power 3/2. And with a minus sign. In the z hat direction. No, sorry. That is r prime, this r prime over here. I'm taking the z hat one, the coefficient z, I can just take it out. Q over 2 pi r squared epsilon 0 in the z direction from 0 to r, the r prime over r prime squared plus z squared to the power 3/2 in the z direction. This is our electric field.
Wasn't there a minus sign?
Well, you see, we had evaluated that this rho hat prime integral is 0. The minus sign is over here. This term doesn't contribute. Its integral is 0. There is only a contribution from this term, and here I have the z hat. I can take it out. There's a z over here. There is an r prime over here. Well, z is independent of r prime, so I can take it out of the r prime integral. There's no minus signs. What is this integral? Yeah, this is an easy one. Don't think about complicated expressions. No.
This is 1 over 3.
Take the derivative of this expression with respect to r prime. So you will get a minus 1/2 minus minus makes plus 1/2 times this same thing with the 3/2 power multiplied by the derivative of the inside, which is 2r prime. 2's and 1/2 will cancel, and we are left with this one. So this expression over here is nothing but the derivative of with respect to r prime of this one. Since it's a total derivative, well, the integral of a total derivative of a function is the difference of that function evaluated at the boundaries. Sure. But since there is a nice r prime over there, it's easy. And it becomes q over 2 pi r squared epsilon 0 z in the z hat direction 1 over z minus 1 over large r squared plus z squared to the power 1/2. Assuming I didn't make any other computational mistakes, this is our result.
Hocam şu cylindrical koordinat açıklaması yaptınız ya, ben oradan itibaren karıştırdım. Şu yukarıdan hocam şey yazdık ya, benim r vektörü r.
So this is just a reminder of what we call how we define the cylindrical coordinates. Let's say this is our x-axis, y-axis, z-axis. We take an arbitrary point. So in cylindrical coordinates, to determine the coordinates of this point, what we do is the z-coordinate is just like in the Cartesian coordinates. You just consider the height from the xy plane. That is the same thing. And then you just take the projection on the xy plane of this point. This is my point. Just bring it straight down parallel to the z-axis to the xy plane. Then the distance on the xy plane from the origin is what I call the small r. Well, I would have preferred to call it rho, but you objected to it. But so we stick with the small r. Okay? And the vector on the xy plane pointing towards this projected point is what I call the rho hat vector. So this is my arbitrary point. I consider the projection on the xy plane. So there is this unit vector pointing from the origin to this projection on the xy plane. That is what I call rho hat. So this point over here, I can just write it as r in the rho hat direction plus z in the z hat direction. Okay, so that is an arbitrary point. I can just write its position in terms of the rho hat and the z hat vectors. So it's r in the rho hat direction plus z in the z hat direction. This is an arbitrary point. Now this r prime vector is not an arbitrary point. It's a point on my disk, which is at z is equal to 0. So the z coordinates of this r prime is 0. Of course, it has some r prime in the rho hat prime direction because r prime point, let's say for r point, I call it the rho hat, but this r prime point, let's say it's some point over here. So it's not the same rho hat vector, it's some different rho hat vector because this r prime vector has a different phi angle. So that's why I put the rho hat prime over here to differentiate that this is the rho hat vector corresponding to r prime. This is the rho hat vector corresponding to r. And then, okay, we already have this general expression for the electric field on the first line. So whatever rho of r is, whatever your charge density is, whichever coordinate system you use, this is the expression for the electric field. Identify rho of r prime, choose a coordinate system, express this vector in that coordinate system, evaluate the integral, and you're done. So that is what we did. Rho of r prime, we had already, corresponding to this very thin disk, we had already calculated this rho of r prime. So I just put, this is our rho of r prime for this problem. And then we just put it in the general expression for the electric field, and we chose to work in cylindrical coordinates. In cylindrical coordinates, this is the volume element. This is the charge density with this factor over here, volume charge density, and this is the remaining vector. Well, using this Dirac delta and the step function, I could evaluate the z prime integral and restrict the r prime integral from 0 to r instead of 0 to infinity. And I obtained this expression over here. Well, now I avoided as much as possible to replace these vectors in terms of their explicit forms, in terms of their coordinates, but now it's time to do that. So in cylindrical coordinates, this is how I would represent these two vectors. There is the r vector. R vector is the point at which I'm trying to calculate the electric field, and the r prime vector is the point at which there is a charge contributing to that electric field. So r vector is an arbitrary point, so it has an r component and a rho component and a z component. R prime vector is a point on my disk where the charges are. So r prime vector doesn't have any z coordinate. It only has the rho coordinate. Well, I have these coordinates written in terms of their components in cylindrical coordinate system. Now I can evaluate their, well, of course, in general, their difference and the distance between them will be a complicated function of phi, z, and r prime. So I just simplified my problem a bit. I'm now evaluating the electric field on the z-axis. Not at an arbitrary point, but at a point on the z-axis. Since I put my electric field on the z-axis, the r point only has the z coordinate, doesn't have the rho hat coordinate, so this is the form of my r vector. That is the form of my r prime vector, so r minus r prime vector. I have two vectors, just subtract them, and this is what I get. Rho hat and z hat, they're orthogonal to each other. So to evaluate the magnitude of this one, just take the scalar product of this with itself and take the square root. If you take the scalar product of this vector with itself, since these two are orthogonal vectors, just like x, y, z, then the square of their magnitude is just r prime minus r prime squared plus z squared. I take the square root to write the magnitude. And now these two, this vector and this magnitude, I just put in my expression for the electric field. So this was the expression for the electric field. I just copied it. And instead of this vector and this magnitude, I substituted the corresponding expressions. Well, now there is nothing else to but evaluate the integrals. I started with the phi integral. I first said that, okay, phi hat prime, let me write it here explicitly again. This is in the x hat direction cosine phi prime plus in the y hat direction sine phi prime. This is what rho hat prime is. If I calculate the phi prime integral, both cosine phi prime and sine phi prime, when I integrate them from 0 to 2 pi over one full period of the cosine and phi, I get 0. So the integral of rho hat prime over phi from 0 to 2 pi is 0. The only thing that depends on phi is this term over here. And the integral of that term over phi is 0, so that's just 0. I'm left with this one only. And, well, basically this is what remains. From this line to this line, I just rewrote some of the terms, made simplifications over here. I'm left with 2 pi. Z is over here, Z hat is over there. And this integral, although it looks complicated at first, but once you realize that this factor over here is nothing but the derivative of this function with respect to r prime, well, the integral is also easy to evaluate. And then we are done. If we have done everything correctly, assuming that our answer is correct, this is the final expression we have. Now let's check if our answer is correct or not. Let's start with units. Is the units correct? Remember, the unit of electric field should be the unit of 1 over epsilon 0 times the unit of charge divided by the unit of distance. Unit of 1 over epsilon 0 is there. Unit of charge is over there. What remains should have the unit of 1 over distance squared. So we have the z, 1 over distance squared is already over here. So basically this term, this piece over here has the units of the electric field. What remains should not have any unit. Well, this has the units of 1 over distance, but it is multiplied with something that has the units of distance. So essentially this is, z times this is unitless, so the units match. There's no problem with the units. Let's consider some other limit. Let's assume that we are very far away. That is, z is much larger than r, or r over z is much less than 1. So this unit basically corresponds to, we have this disk over here, but it's so small that it looks like a point. Well, if it is a point, then we already know the electric field of a point. So if this is correct, then the electric field should be equal to 1 over 4 pi epsilon 0 q over z squared, if r goes to 0. Let's try to show that this is actually true in the z hat direction. Do you agree that when z is very large, much larger than the size of the disk, this should be the electric field? Do you agree or disagree? Okay, you agree. One nod, 2. Others? You agree. 3.
Şimdi hocam şurada z yerine infinity koysak.
Well, you see, if you put infinite, then the electric field is 0 anyway. So that's not really the way. And we have to make some kind of an expansion. Well, z is large, but 1 over z is small. So we have to kind of make an expansion in r over z, which is very small. We will do Taylor expansion. And we will show that the first term, non-zero term, should be equal to this one. Now, this is not, I didn't drive this looking at this result. I ignore that result, but what do I know? I have this disk, which is very small, I don't know, at 1 kilometer. It has a disk of radius, let's say 1 centimeter. From where I look, it just looks like a point. I mean, unless I have some binoculars, there is no way that whether I can tell it's a disk of radius 1 centimeter or just a point. It should be true even for the electric field. It should be true for all the properties of that disk, if I am very far away. So that is my claim. And if my result doesn't satisfy this limit, then the possibilities are either this result is not correct, then I learned something, I learned how to correct my calculation, I need to correct my calculation, or my expectation was not correct for some reason. Well, that would mean that I have some wrong understanding of what is going on, so I should correct it, so I will still learn something if this is not satisfied. Well, if it is satisfied, if this limit is satisfied, that will be kind of the most boring limit. I will not learn anything. I will just confirm that my answer is likely true. Let's check this limit before they kick us out. So let's see, I know that 1 over r times rz is very small. That is what I will use. So the electric field that we calculated is q over 2 pi r squared epsilon 0 in the z hat direction. Now let me multiply with z. It is 1 minus 1 over 1 plus r squared over z squared to the power 1/2. Or let me rewrite it, q over 2 pi r squared epsilon 0 in the z hat direction, 1 minus 1 plus r squared over z squared to the power minus 1/2. This is my result. Now I will use the so-called the binomial expansion, which is just a special form of the Taylor expansion. 1 plus x to the power of an arbitrary number, and it can be real, imaginary, positive, negative, whatever the value of n is. This will be approximately equal to 1 plus n times x plus higher order corrections terms that are proportional to x squared, x cubed, etc. Well, if x is very small, then I can just keep the first term. The other ones will give negligible corrections. Well, in our case, we are looking at the limit that r over z is very, very small. So it will be enough to keep one term. This is equal to q over 2 pi r squared epsilon 0 in the z hat direction, 1 minus 1 minus 1/2 r squared over z squared plus other terms that I ignore. Well, this 1 will cancel this 1. I have minus 1/2 minus makes plus 1/2, 1/2 times 1 over 4 pi. Well, I have 1 over r squared over here. It will cancel that 1 over r squared over there. So this is equal to 1 over 4 pi epsilon 0 q over z squared in the z hat direction. Plus, there are other corrections in this expansion. But at least the first non-zero term, if we are sufficiently far away from our disk, does coincide with what we expected. So at least at this point, there is nothing that would make us suspicious that we might have made some mistake in the calculation. The units match. The certain limits that we could actually test, they coincide, so most probably we didn't make any mistake. Yes, any last questions before you go? Okay, so see you on Friday, right?